All right, welcome to The Explainer. Today we're going deep inside something that powers our world but that most of us never see. We're going to break down the anatomy of a massive industrial plant to find out what really makes it tick. Let's get right into it.
I mean, really think about that. How is it even possible? You've got all this colossal machinery, all moving in perfect sync, all day, every day. It's not magic, not at all. It's an incredibly well-designed system, a kind of unseen machine that's engineered with insane precision. And today, we're going to take it apart, piece by piece.
So to really get it, we're going to look at this whole thing like it's a living, breathing creature. First up, we'll check out its muscle, the raw power behind it all. Then we'll trace its nervous system. That's the network that carries all the messages. After that, we get to meet the brain, the smart automation that's calling all the shots. And finally, we'll look at the safety net that makes sure it never, ever fails. Okay, so every giant machine, every massive operation, it all has to start with one thing: power. And we are talking about a serious amount of it. This is the very heart of the plant, pumping life-giving energy to every single corner. The whole operation is humming along on 3,000 volts. Now, to put that into perspective, the outlet in your wall is probably, 120 volts? Maybe 240 if you're lucky. This is a whole different league. This isn't just power, it's the industrial-scale lifeblood for the entire facility.
Now look at this. And don't worry, you don't need to understand what every little line and symbol means. The point here is just to appreciate the sheer complexity of it. This is a real schematic, and it really does look like a circulatory system, right? Just this incredibly dense web of arteries, all channeling that high voltage power exactly where it needs to go.
So how in the world do you safely control 3,000 volts? Well, you use something called switchgear. And the easiest way to picture it is to think of the biggest, baddest fuse box you can imagine. It's basically a massive switching center, full of heavy-duty circuit breakers that are designed to handle these huge electrical arcs, so you can safely send power where it's needed or shut it all down in a heartbeat. So we've got the muscle. But, muscles are pretty useless if there aren't any signals telling them what to do. That brings us to the plant's nervous system, this amazing network that lets all the different parts talk to each other.
And just like our bodies, this plant has different kinds of wiring for different jobs. On one hand, you have these thick, beefy power cables. Those are the arteries carrying all that raw, high-voltage power. But then you have these much smaller control and signal cables. Think of these as the delicate nerves, carrying these tiny 24-volt signals and little packets of data that are actually the commands and sensor readings.
But for this nervous system to really work, it needs a language. And that's where you get these industrial protocols, like Profibus and Profinet. You can think of them as super fast, ultra-reliable languages built just for machines. They run on redundant fiber optic networks, which means there's always a backup path. It's all designed to make sure that commands and data get from the brain to the limbs instantly and without a single interruption. Okay, we've got the power, we've got the network. But what's actually making the decisions here? What's taking in all this information and turning it into smart, coordinated action? Well, it's time to meet the brain of the operation.
And that brain is a PLC, a programmable logic controller. Now, this isn't like your laptop. This thing is a beast. It's a hardened, super tough industrial computer built to live in a really harsh environment and just run 24/7 without ever complaining. Its entire job is to slurp up thousands of signals from sensors all over the plant and then execute a program to control, well, everything.
So what's a day in the life of a PLC look like? Well, it's all about cause and effect, constantly. This table shows you some real-world examples. So let's say a little sensor sends a signal screaming, "Hey, this chute is totally full." The PLC instantly, without even thinking, commands the conveyor that's feeding it to stop. Or if a belt rip detector goes off, boom, it triggers an emergency stop for everything connected to it. It's this non-stop, high-speed conversation happening every single second.
But the PLC isn't just reacting to problems, it's also proactively brilliant. Take starting up a long line of conveyors. You can't just flip one big switch. You'd have a catastrophic pileup of material. No way. The PLC is programmed with this perfect interlocked logic. It actually starts the last conveyor in the line first. It waits for the signal that it's running at the right speed, and only then does it start the next one up the line, and so on and so on. It's this beautiful, intelligent cascade that prevents disaster.
So this system is powerful, it's connected, it's smart. But what if something goes wrong? I mean, in an environment this big and this complex, failure is just not an option. And that's where the ultimate safety net comes in.
This right here is one of my favorite little details of the whole design. You see these two identical boxes? They're two completely separate, independent power supplies for the PLC itself, for the brain. It's what they call a 2x100% design. It means one is running the show and the other is just sitting there on hot standby. If the main one hiccups for even a millisecond, the backup takes over instantly. There is zero downtime. The brain can never, ever go dark.
And that's just one piece of the safety net. That PLC is programmed to be a paranoid watchdog, constantly on the lookout for dozens of potential issues. Is a conveyor belt starting to drift off center? It'll send an alarm. Is a motor getting a little too hot? It knows. Is a chute about to get jammed up? It can actually stop it before it happens. It's even tied into the fire alarm system. It's like this digital immune system, just waiting to pounce on a tiny problem before it can ever become a big one.
So what's the whole point of all this? The power, the network, the brain, the fail-safes, why go to all this trouble? Well, this quote from the original design document says it all perfectly. The goal is to ensure the safe, long-term, and stable operation of the equipment and to lower labor intensity. It's all about making things safe, making them reliable, and making them efficient.
You know, when you flip a light switch and the light just comes on, or when a package just shows up at your door, or your tap water just runs clear, you're seeing the end result of a system just like this one. Incredibly complex, almost totally invisible, and engineered to be flawless. So the next time something in your life just works, take a second and think about the unseen machine humming away quietly in the background, keeping your world in motion.